Hello, my name is Lauri Himanen, and I'm part of the NOMAD development team. And basically, I'm just going to pick up from where Marcus left off. So he already told you about what these plugins are. We have two different types. We have this Python schema plugins and parser plugins. And my presentation is all about these Python schemas. I'm just gonna like highlight like a real life use case for where you could use these Python schemas in, for example, in a lab. And I hope this gives you like an idea of what you can do with these. So there's quite a lot of functionality you can now add to your Nomad installation with this. So briefly, the overview is that I'm gonna like explain a small, like kind of a fictional use case for a lab that somebody might have, and how you would digitize your workflow with these Python schemas. Then I'm gonna talk more about what these schemas actually look like. So I'm gonna like maybe already Marcus mentioned a lot of these technical details and what the Python code looks like. I'm gonna give like a bit more in-depth information on this. Then we'll have a demo. So we'll actually like use this kind of a schema on locally on my system. I'm gonna show you what it looks like, what the code looks like, and things like this. And yeah, depending on how much time we have, I might talk something about these YAML schemas versus Python schemas, and then we'll like recap everything that we covered here. So let's just start with this like a use case that I've created for this presentation. So imagine that you have a lab that performs some kind of measurements, in this case, bandgap measurements on thin film samples. And you want to make your data fair by using NOMAD Oasis as a research data management platform. So basically you have a NOMAD Oasis installation within your premises, but it kind of it's not flexible enough to really fulfill like and cover and capture your workflow. So how can you now start customize your Oasis installation using this plugin mechanism? Basically, what we've seen is that there is no one size fits all Oasis setup that would suit every lab. So that this is why the customization is important. And this is where the schemas come in. With these schemas, Python schemas, especially, you basically are able to completely customize the way entries are created within Nomad. And just to like highlight the difference between these two plugin types, already Marcus covered that pretty well, but essentially schema is something where which a user actually manually chooses, and then you can also manually edit the entry contents, whereas a parser is fully automated. So it will just look at some file type, some information on files on your disk, and fully automatically populate entries based on it. So this is like I would say the main difference between schemas and parsers. And essentially what the schema does in terms of like this kind of a UML diagram, there's one schema which can basically spawn multiple entries, and each entry has one associated schema with it. So there's this one-to-n relationship between these two. And if we just wanted to like briefly comment on what we would want to have from these schemas in this lab example. For example, as a Nomad user in this lab, I want to instantiate these kind of new entries through the GUI that follow this custom schema that is especially designed for the lab. And as a Nomad user, I want to also upload some data files. So for example, if we're talking about measurement devices, they typically produce some files. So I want to upload these into my Oasis and have some sort of a linking to samples, maybe some post-processing. As a plugin developer, so maybe as within your lab, you have a person that is responsible for this development. You want to be able to automate some of the tasks. So you put some functionality into the schemas that kind of make the life of the researcher easier. So maybe there's some post-processing steps, maybe some fields are filled automatically and things like this. And also the Oasis typically has an administrator as well, who is then really responsible for setting up the schema for the Oasis, installing it correctly, and also responsible for keeping it up to date. So these kind of user stories you could come up for this use case. And now let's take a look at what the schema structure actually looks like. So Marcus already covered this pretty extensively. We're gonna go over it again as a kind of a recap here. So essentially these Python schemas are just regular Python classes that define how an entry will be instantiated in Nomad. So they really define what kind of data it can contain. They can also define how these entries will look like in the GUI to some degree, and how it will be processed. To give you like a very rough overview of how these are associated with each other. So if we have a schema here, so you can see it's just a Python classes, a similar example that what Marcus showed as well. So this is our schema, and with it you can instantiate entries. Here I've given an example of an entry serialized in JSON. So this is our actual data that kind of conforms to this schema now here. And if you view this kind of an entry in the GUI, basically the GUI uses information both from the schema and the entry to give you a view on it. So this is kind of how these different entities within Nomad are connected. And now if we start to like break down this Python class a bit more and take a look at what it is constructed from. So essentially we use the Nomad meta info concepts, as Marcus mentioned, to define the data layout. So in the Nomad meta info, we have these things called sections, which are essentially just containers for information. So here you can see a section called substrate, which essentially just is a container for this actual quantity, which is like an actual concrete piece of data. So this is how you can, with the sections, you can introduce hierarchy into your data, and quantities are actual concrete data items like strings and floating point numbers and so on. And what you can see here as well is this package. And essentially, we can see here that we have kind of wrapped our schema around this package definition. It basically just gives you your own namespace for the schema, so that it's separate from all the other schemas that other people may have defined. So these three things are quite important in the schema development: sections, quantities, package. And you can see here that essentially this class will be our new schema, and it has to inherit from entry data. It can be like direct inheritance. There might be some classes in between, but essentially this gives you like now access to all this. It tells Nomad that this class should become a schema, and it can instantiate entries. We provide some base classes for you. So this entry data is the most basic one. There are some more customized one in our code base already, but essentially it's up to you. You can create completely custom ones or use some of our own base classes that we provide. And yeah, as I mentioned, the data is captured in sections and quantities here. And later on, we'll see a bit more of an example of these annotations, which basically tell how the GUI is supposed to display certain quantities, for example. So basically, with this, you have the possibility to define completely new meta info fields and customize your schema quite heavily. So you can have all kinds of information that is kind of really specific, for example, to your lab and your workflow in that lab. But there's you should also keep in mind that all of these entries also have this kind of shared common part of the meta info. For example, in this, you can see there's this section called results, which contains things like properties, electronic properties. There's the material definition and so on. So these are kind of available to you. And how this can be useful for you is that if you fill this common part of the meta info, you kind of are enabling interoperability with other entries. and also kind of a deeper integration into Nomad. So because this common part is something that everybody knows about and our GUI knows about and so on. So there's like different tooling and different interoperability tools that now kind of activate if you feel this layer. So we're gonna see like an example of this as well. And now maybe the most important part of these Python schemas is like where they also differentiate from the YAML schemas is this normalization. So these classes may now define a new method called normalize, where you can just basically run any kind of Python code. And this is like really that kind of unlocks all these superpowers that these schemas can have. So these are triggered whenever data is changed. So whenever you create a new entry, you save it, modify it to some degree. All kinds of default actions could go in here. For example, we can see an example here, like if there was no institute defined in this schema, we fill it with a default value so that the user doesn't have to fill it always. There can be some post-processing steps, like if you have a file associated with this schema, maybe there's some post-processing on the data in there. Basically, it's just any Python code. And you should notice that these normalized methods from the parent classes are also available. So you can just basically with this syntax, you can call the normalized method from the parent class as well. And with this, you can kind of hook into the any actions that the parent class has defined as well. So there's this inheritance of the schemas and these normalized functions as well. But yeah, you really have to be careful, and this is really also the key point why these Python schemas are plugins, because you can run almost any kind of Python code in here. So you have to be kind of careful that you don't accidentally remove data, overwrite data, you don't do anything nasty in there. But there's great flexibility, but you have to be really careful as well. And as Marcus mentioned, basically these schemas are Python packages essentially. Typically, they live in Git repositories. And you can install them in this way that Marcus explained as plugins. So in your Nomad installation, you have this nomad.yaml file, and then you can just define these Python packages in there to enable to mount them into your installation. So let's jump into like an actual demo that kind of showcases this use case that I was kind of hinting at. So we were now kind of imagining this lab workflow where we have some researchers who run a few machines in a lab, and they want to now kind of digitize all of this information that you're capturing from these devices and what you kind of know as a researcher. So let's set up some requirements that we want the schema to do. So we want to some fields for what the sample ID was, what institute you're working in, what was the timestamp when this sample was created. And we want these to be filled kind of automatically or semi-automatically at least. And now let's say the lab performs this kind of X-ray fluorescence spectroscopy to kind of just identify which elements are within a sample. And this, in my example here, this basically is just a file which contains the information, and we want the normalize function now to kind of extract these elements from it and put into our data. And also the lab then performs another measurement, like this kind of a UV visual spectrum measurement to measure the band gap of this sample. So this produces another data file that you might want to associate with your entry, and we want to kind of automatically extract the band gap value from this. So these are kind of the kind of ideas that we have. And now let's take a look at what this kind of example would look in real life. So I have a custom installation running here with this my custom schema attached to it. You can see that we have the schema code in here. It's not super long. I've tried to keep it as simple as possible in here. So it's only 75 lines roughly. We can see that there's some new quantities that I've defined in here. But let's kind of tie these to what you see in the GUI. So as Marcus showed, once we have these schemas attached to an installation, you can essentially find them from here. So you can see that my example is called my sample. You can see it here. The name is here in the code as well. So I want to now instantiate like an entry from this. Let's call it my sample one. So now we are really creating this entry in here, and then there's a bunch of things that are appearing here. So let's kind of break down what these mean and where they come from. So you can see that our custom schema, first of all, it defines a few new quantities here. We can see that there's an actual string quantity for the X-ray fluorescence file. And this is like a good example of these annotations that I hinted at previously. So we have given an annotation that essentially says that this is a file, and there should be this kind of a file edit component shown in the GUI as well. So basically it means that you get this button through which you can actually then upload a file. So let's do that right now. Also, you can see that there's another quantity for the UV spectrum file. So this comes from some other device, for example, and it looks kind of the same. It also has this kind of upload functionality in here. So let's just upload this here as well. So these are the two new quantities that we had defined in the simple schema, but where do all these other things come from? So you can see that this particular schema inherits from this sample class that is part of Nomad installation. And you can see that inside it, we already have defined some quantities that are kind of typical for a sample that could live in a lab. So there's, for example, an ID, name, date, time, institute, description, and these kind of match with what you see here. So these, from this base class, all of these quantities are kind of inherited for my schema, so I don't need to repeat them here. Now, if we turn on to the normalize section where the interesting parts are happening. So you can see, for example, here that upon creating this entry, some of these fields were pre-populated. So for example, the sample ID you can see is pre-created here. And this is what the normalize function is now configured to do. So you can see that it calls this parent class normalize method, but this is not doing pretty much anything at this point. But what we are defining in addition is that if institute was not defined, I want to set a default value. So you can see the default value being populated here. The same thing for the date time. It's just set to the creation date time. And a sample ID, I've just kind of given an example where maybe in your lab, you just want to create this random sample IDs that are kind of guaranteed to be unique. And we populate with this. So that's like a simple example of what this normalize function could do. Just pre-populating some default values in there. But now let's take a look at what other interesting things are happening in here. So we can see that our schema is actually now configured so that if it sees that this X-ray fluorescence file has been set, it is going to read this file and it's going to do something with it. In this case, what it does is very simple. So if we take a look at what this looks like, so this is kind of a very primitive example where the file is just a list of elements and their concentrations. So this is not probably what a real X-ray fluorescence file would look like, but this just gives you an idea of what is possible. So in this case, we just load this array of data. We take the first column in here and we extract the elements. And one thing you can see here is that we are actually now putting these elements not into our own schema. So there's nothing related to elements in our schema here. We are actually populating this kind of common part of these entries. So every entry has this results part in here where there is something called material. We are populating it in here. So let's see actually what happens once we press save. So we will see that this has been now populated with the elements read from this file. So this is like a super simple example of what you could do. It's just reading a data file and storing some data from it into this common part of the meta. So now if we take a look at what we are doing with the UV vis spectrum file, so this is kind of more advanced example. It's maybe not realistic still, but at least a bit more advanced. So here we have a spectrum data that roughly looks like this. So there's the orange raw data, which gives you the absorbance as a function of wavelength. And now what this normalize function is doing is that it is, first of all, reading this data. It's smoothing it with this kind of a filter from SciPy package. And then it's calculating the gradient of this thing, which is given here in blue. And from the peak in this gradient, it's kind of locating the bandgap. So this is like a very simple example, maybe a bit naive way of getting the bandgap value here, but it demonstrates that you can really run kinds of advanced post-processing on these files to get something out. So what it does with this information then is that it gets the wavelength corresponding to the bandgap location, and it transforms this into energy, and like an actual energy, bandgap energy. Well, you can see that we are using this unit system from NOMAD. So we have this own custom unit registry where you can get all kinds of unit conversion tools. And once again, we are simply storing it into this common part of the meta. So you can see that we already have kind of a specified default location for bandcaps, and it lives under results properties, electronic, span structure, and bandcap, where this value lives in. And we can see that we are essentially just populating it here with this value. Now, basically, this is an example of what a kind of a more advanced normalization would look like. And what you can kind of imagine now as a person living in the lab is that now you can do all kinds of interesting things with these samples. So here's an example of where I have pre-populated these similar items, a lot of them from different locations. You can see that they all inherit now from this custom schema that I have defined. And what kind of interesting things you get from these schemas is, first of all, you can search for all these custom data items that are really specific to your schema. So it's like these 5 now, in this case, are kind of really the live in your schema namespace. So you have this spectrum files, the sample IDs and institutes, and you can perform some kind of simple queries on them. You could, for example, search for a specific sample ID and so on. But what it might be more interesting and more like advanced is that because we have filled this common part of the meta info under this results. So for example, we filled the bandcaps under there. You get like this added functionality that we have built on top of it. So for example, you could build a histogram for these bandcap values directly with the GUI. So the GUI is kind of, it knows about this location, it can connect to it, and it can build all kinds of queries and visualizations. So now we could, for example, if we know that my lab produces thousands of them, you could search for different samples based on the bandcap value that is reported, and you can see the results updating here live. The same thing that you can now do with the periodic table. So you can see which elements are available in here. You can click and filter based on the elements. So you get kind of more interoperability with our search tools and all kinds of visualization and search query capabilities directly out of your schema if you use this common part of the method. And then you can imagine that for a lab who wants to digitize this kind of a workflow, this is a really powerful tool to capture their data and search for it, and then ultimately, hopefully, also share it. So this kind of ends my demo here. I think I'll just briefly maybe go over a few more things quickly here that I wanted to show, because my time is pretty much, I think, running out. So what I want to emphasize is the difference between these Python schemas and YAML schemas. So what we have discussed here is a Python schema. It is implemented as a Python class, it's Python code, and it is part of an Oasis installation. NOMAD also allows you, like Marcus mentioned, you can define these YAML schemas, but these are really, they're considered to be a part of the data. And the main differences here is basically that Python schemas are a plugin, whereas YAML schemas are not. Python schemas allow you to define new Python code and allow you to run these normalized functions, whereas these YAML schemas there, you cannot define new Python code to run, but you can kind of attach to these normalization of the existing base classes. So if you say that your YAML schema inherits from some base class, those normalization functions are still going to be run, but you cannot define anything new in these. And both of these can basically be used to extend existing base classes. But the difference with the Python schema is that this really must be installed by an Oasis administrator and must be kind of accepted by the administrator, whereas these YAML schemas can be uploaded by anyone because they're kind of not as dangerous, but also not as powerful as the Python schema. Just to quickly recap, what I've been talking here is that the schema plugins really allow you to customize your Nomad installation. You really get full control on how data gets converted into entries. You can define your custom data layouts. You kind of have this your own namespace within our meta info where you can do all kinds of things. But you really should also utilize the common part of the meta info to integrate with the tools that we are developing. The community is kind of expecting, and you're kind of enabling also interoperability by using these as much as possible. The Python schemas can execute code to perform all kinds of actions, but yeah, you really have to be careful when you're developing these things so that you don't do anything destructive, for example, in there. And it is possible to update your schema later. And this is kind of also important so that, for example, if your lab has performed measurements the last year, and now you figure out that, okay, maybe the schema could be improved, you just upload a new version of your schema, and then you can reprocess your existing entries to kind of just reprocess them and get this new schema functionality out of it. So this is also, I think, an important part of these schemas. Basically, with this, I thank you, and I will take any questions that you might have related to these Python schemas.